Welcome to my tutoring session in chemistry. In this video, I'll talk about column chromatography. The current video is part 1 of the 3-part series in column chromatography. I'll explain the principle involved in chromatographic separation by column chromatography and the intermolecular forces that are operative between the molecules and the stationary phase during the column chromatographic separation. What is chromatography? Chromatography is a separation technique where the given sample mixture is separated into individual components using a stationary phase, which is usually a solid silica gel, and stationary phase, it is a non-moving phase, and mobile phase, which is a moving phase, and it is a liquid solvent. So chromatography is a separation technique where the given sample mixture can be separated into individual components using a stationary phase and a mobile phase. Now, how do you prepare the stationary phase? You prepare a suspension of the silica gel using the recommended solvent and pour it over the glass plate to get a thin layer of silica gel that acts as a stationary phase. Now, the glass plate acts as a solid support while the applied silica gel layer acts as a stationary phase. Now, the TLC plates are commercially available. There are two types. One is glass backed silica gel plates. The other is the aluminum backed silica gel plates. Now, it is more convenient to use the aluminum backed silica gel plates as it is flexible. It can be easily cut using scissors. It can be rolled so as to fit into the chromatographic chamber. Now, the thickness of the layer for analytical plates is around 0.25 millimeters, and for preparatory plates, it ranges from 0.5 to 1 millimeter. Now, so much for the TLC stationary phase. Now, what about the column chromatography? Now, column chromatography is one of the chromatographic techniques where the given sample mixture is separated into individual components using a stationary phase of silica gel slurry that is filled into the glass column. Now, the glass column acts as a solid support to the silica gel slurry that is filled inside the glass column. Now, the sample mixture is separated into individual components using the stationary phase silica gel slurry that is supported by the glass column and the mobile phase that travels down the column by gravity. Now, the development in case of TLC is by ascending technique where the solvent or the mobile phase, it moves or travels to the stationary phase by capillary action, and in the process the sample gets separated. Now, both the techniques work on the same principle, that is adsorption. HPLC columns and columns used for gas chromatography are far more superior in performance as compared to the conventional column chromatography. Now, both TLC and column chromatographic techniques, they are interrelated. In case of TLC, the solvent or the mobile phase, it travels up the stationary phase by capillary action against gravity. While in case of column chromatography, the solvent or the mobile phase, it travels down the column assisted by gravity. And both work on the same principle, that is adsorption. Now, the given sample mixture can be separated by both the techniques, TLC as well as column chromatography. Now, in case of TLC, you draw the baseline at the lower end of the TLC plate, apply the sample using the glass syringe or a capillary, introduce the TLC plate inside the TLC chamber. And when you're introducing the TLC plate inside the chamber, make sure that the level of the solvent is below the baseline where the sample is applied. Now the schematic that you see is wrong way of carrying out the development of the TLC plate. Now here in the schematic shown, you can see that the baseline on which the sample is applied is submerged. It is totally submerged in the mobile phase. So the sample will be washed away and there will be no separation. So the right way of doing it is to maintain the level of the solvent slightly below the baseline over which the sample is applied. Now during the development process, the solvent or the mobile phase, it moves or travels up the TLC plate by capillary action, and the flow of the mobile phase is against gravity. While in case of column chromatography, the solvent is flowing downwards, that is, it is assisted by gravity. So this is the major difference between the TLC and column chromatographic technique. So in case of TLC, the solvent is flowing upwards against gravity, while in case of column, the solvent or the mobile phase is flowing downwards, which is assisted by gravity. So when you turn the TLC plate upside down, the technique resembles that of column chromatography. So both the techniques are interrelated. Both TLC and column operate on the same principle of adsorption. In case of TLC, solvent flows against gravity, while in case of column technique, solvent flows with gravity. In case of TLC, the non-polar component is very close to the solvent front, while in case of column technique, the non-polar component is the one that comes out or eludes the column first. Now we make use of glass column for carrying out the separation by column chromatography. Now the stationary phase, that is silica gel, it is introduced inside the glass column by two methods. One is the dry packing method, other is the wet packing method. Now in case of dry packing method, the silica gel powder is introduced inside the column in its dry form, and this is followed by the mobile phase inside the column. So first the column is filled with the dry silica gel powder, and this is followed by pouring the mobile phase from top of the column. So when you do this, air bubbles gets trapped and this leads to cracking of the column. So this is the major drawback with case of dry packing method. Entrapment of air bubbles, which ultimately cracks the column. And therefore the widely employed or preferred method is the wet packing method. In case of wet packing method, first you prepare the silica gel slurry by dissolving the silica gel powder in the recommended solvent, stir vigorously using glass rod, and then fill the glass column with the slurry of silica gel, and make sure that the level of solvent in the glass column is slightly above the silica gel layer. So in case if the solvent, it goes down the silica gel or below the silica gel layer, it leads to absorption of moisture by silica as well as drying of the column, and ultimately the column cracks. So introduce the sample mixture at top of the column. So this is called loading the column with the sample mixture. And the solvent, it flows down the column by gravity, and you can collect the solvent fractions using Erlenmeyer flask. So the solvent, it flows down the column by gravity, And with the flow of the mobile phase down the column, the sample mixture introduced on top of the column, it gets separated into individual components depending on its relative affinity towards the stationary phase, that is silica gel. Now the component that has weaker affinity towards the stationary phase elutes the column or comes out of the column first, and you can collect the fractions using a conical flask or a test tube. And this will be followed by fractions of lesser affinity towards the stationary phase. And the component that is coming out of the column last will be the one which is having a stronger affinity towards the stationary phase. So this is the TLC profile of the separated components. And in case of TLC, the solvent flux, it flows through the stationary phase against gravity by capillary action. While in case of column technique, the solvent flows with gravity. And when you turn this TLC plate upside down, it resembles the column separation. Now the solvent that is used for the separation is called eluent. The components being separated is called elevate, and the separation process is called elution. Now there are two types of elution techniques. One is isocratic elution, other is the gradient elution. In case of isocratic elution technique, solvent of same strength and polarity is used throughout the separation process. For example, only hexane can be used or only ether can be used throughout the separation process. Or if you are using a mixed solvent like hexane ethyl acetate in the ratio 9:1, you are supposed to maintain this ratio throughout the separation process. So when you maintain the ratio, polarity will be maintained. Now, in case of gradient elution, solvent system of gradually increasing polarity is used. Say for example, you're using hexane ethyl acetate solvent system in the ratio 9:1. Now gradually you can change the proportion. As you change the proportion to 8:2, 7:3, 6:4, 5:5 and 4:6, you can see that there is change in the polarity. So in gradient elution technique, solvent system of gradually increasing polarity is used. While in case of isocratic elution, solvent of same strength of polarity is used throughout the separation process. So iso means same, gradient means gradual change. Here it is referred in terms of polarity, solvent system. Now let's try and separate three molecules of varying polarity using a non-polar mobile phase, which is a mixed solvent comprising of hexane and ethyl acetate. Now hexane is a totally non-polar molecule, while ethyl acetate is a solvent of intermediate polarity. So we have a polar stationary phase inside the column filled with silica gel. Now silica gel, it is polar in nature due to the presence of silicon groups. Now silicon groups are characterized by hydroxy groups covalently bonded to silicon. So we are trying to separate three molecules of varying polarity: a polar paracetamol molecule, acetophenone which is of intermediate polarity, and a non-polar naphthalene molecule. As the solvent or the mobile phase travels down the column, the components of varying polarity, it moves down the column. So paracetamol moves or covers a shorter distance down the column. This is followed by acetophenone, and naphthalene being the non-polar molecule, it travels down the column and it covers a longer distance. Now naphthalene being a non-polar molecule, it interacts strongly with a non-polar mobile phase, that is hexane, by van der Waals interaction or van der Waals attraction. So it is the van der Waals attraction between the non-polar naphthalene molecule and the non-polar hexane molecule which drags it down the column at a faster rate. While in case of polar molecule like paracetamol, the hydrogen bonding interaction between the polar silicon groups and the heteroatoms present in polar paracetamol molecule holds the molecule and prevents it from flowing down the column freely. While in case of molecule of intermediate polarity, that is acetophenone, you see that there is weak hydrogen interaction, as there is only one oxygen atom to interact with the polar silicon groups by hydrogen bonding. Whereas you find little bit of van der Waals interaction with the non-polar hexane molecule. So the non-polar groups like the methyl group and aromatic ring present in the acetophenone, it strongly interacts with non-polar naphthalene, non-polar hexane molecule by van der Waals attraction. While in case of paracetamol, there is a very weaker van der Waals attraction, and that is due to presence of aromatic ring. So polar interaction by hydrogen bonding dominates in case of polar paracetamol molecule. So as the solvent flows down the column by gravity, you can see that the components are getting separated into individual fractions depending on its relative affinity towards the stationary phase. So as you come down the column, the hydrogen bonding interaction decreases while the van der Waals attraction increases. So the sample mixture is separated into individual components based on its relative affinity towards the stationary phase, that is silica gel slurry in the column. And the component that is coming out or eluting out of the column first is the least polar molecule. So naphthalene being a non-polar molecule, because of its very good van der Waals interaction or attraction with the non-polar mobile phase, it is dragged down the column faster rate, and therefore naphthalene will be the first molecule to be eluted out of the column. So this will be followed by molecule of intermediate polarity, that is acetophenone, and the component that is coming out of the column at last will be the highly polar paracetamol molecule because of its stronger interaction with the stationary phase, that is silica gel. So this is the TLC profile of the sample mixture, which is color coded. Red refers to paracetamol, pink refers to acetophenone, and blue spot refers to non-polar naphthalene molecule. And the TLC development is against gravity, where the solvent flows by capillary action. And when you turn this TLC plate upside down, it resembles the column. Now the principle of separation for column chromatography is adsorption, and the separation of the molecule is based on the adsorption of the molecule on the surface of the solid stationary phase, that is silica gel. As the solvent descends the column, that is as the solvent comes down the column, the sample or the molecule is distributed between the moving liquid phase, that is the mobile phase, and the stationary solid phase. So it is the intermolecular forces that govern or dictate the migration or movement of the molecules in the column. And the zones or bands in the column, what you see, is known as the chromatogram. So the resultant zones or bands is generally referred to as the chromatogram. Now silica gel is highly polar because of presence of silicon groups. First the molecule gets adsorbed onto the polar silicon groups, and this will be by adsorption. So first the molecule gets adsorbed onto the polar silicon groups in silica gel, and as the solvent flows down the column by gravity, it displaces the adsorbed molecule onto the active binding sites of silica gel. So there is displacement of the molecule from the active sites to which it is binding, and this is called desorption. First adsorption, this is followed by desorption due to the solvent flow, and again the molecule will get adsorbed onto the silica gel. So this cycle of adsorption, desorption and adsorption, it repeats until the solute or the molecule comes out of the column. So once the column comes out, the molecule comes out of the column, this cycle ends. So there is a competition between the stationary phase and the mobile phase for the molecule being separated. So the four major intermolecular forces governing or dictating the separation of the molecules by column chromatography are hydrogen bonding, dipole-dipole interaction, coordination, and van der Waals forces. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.